This lesson is on reaction stoichiometry. You should have seen this in a past chemistry class. Hopefully, you remember doing it. But if not, I will give you my lesson on how to ace this section. Previously, from section 4.1 in my lecture notes on D2L, I hope that you are confident with balancing equations. This is important because we want to find the mathematical relationship between substances that are also called compounds or reagents. How many molecules of one reagent is needed to react with the molecules of another reagent to form the product, and how many molecules we can make of the product? We can't easily measure one molecule, but we can measure the mass of substances with a balance and then relate it to the mole. The mole of each reagent can then be related. Remember that 1 mole is a unit that equals 6.022 times 10 to the 23 molecules. To know the number of molecules in a reaction is not meaningful, but to relate the mole back to grams will be very useful. Go ahead and do a stoichiometry related question. First, remember there's key requirements. Understand how to convert between grams of a substance to a mole of substance using the molar mass. One thing that you need to remember is the molar mass is defined as number of grams of substance in 1 mole of that substance. So we have grams of substance in 1 mole of substance, grams per mole. In converting between the units, this triangle is quite useful. We have 3 sections, grams on top, which is the mass, then moles on the bottom, and then grams per mole. Now, in order to use this, you take grams divided by mole, that gives you the grams per mole. If you want grams, you take the mole times the grams per mole to get the grams. Now, if you want the moles, you take the grams and you divide by grams per mole, that'll give you the mole. We'll use the unit conversions as a way of making sure that this is correct. Okay, so another key requirement is when you look at a stoichiometry related question, you have to make sure the chemical reaction or the chemical equation is balanced. Then I want you guys to set up a table to organize your data. It is easier to keep track of your data if it's organized in a table. And then we'll confirm this triangle by using the unit conversion route by canceling out units that match in the numerator and denominator. Questions that are asked in stoichiometry related questions is given here in my 5 points. But let's take a look at this reaction where it's called a redox reaction. Of course, you don't need to know at this stage. You will in the future. What we have here is potassium, K, reacts with magnesium bromide, MgBr2, and it produces potassium bromide and magnesium. Okay, so now let's take a look at one of the first questions, is that we want to know how much of a reagent is going to react with another reagent. In this case, we're going to find the grams of magnesium bromide required to react completely with 5 grams of potassium bromide. Now I set this up in a table like this, and what I want to show you is how to fill this table up properly. Okay, there's a couple of things that you have to remember. Is again, we have potassium, magnesium bromide, and magnesium. And I put down the periodic table down here. I'm gonna help you locate some of these reagents because that's probably the hardest part in chemistry at this point, because it's like a treasure hunt looking for these elements. So what we have here is molar mass. Now in the molar mass, remember it's grams in 1 mole. So we're looking at the molar mass of potassium, not 2 potassiums. We could fill this out by looking for potassium in the periodic table, and it's right here. When you find this, the number at the very bottom is a decimal point. That's the number, that's called the average atomic mass unit. And if we had 6.022 times 10 to the 23 molecules of this, then 1 mole of it would be 39.1 grams. So that's what we want to do is for 1 mole, not 2, we want to put 39.1 grams per mole. Okay, so remember, it's only per mole, and 1 mole of potassium would be 39.1. We do not want to multiply this by 2 because it will ruin the calculations later. Magnesium bromide. Okay, magnesium would be found right here as I point my arrow, and that is 24.3. We could use we could either use 2 decimal points or 1 decimal point. So we got magnesium, and now bromine, Br, would be found over on the right-hand side of the periodic table, right here at 79.9. So what you need to do is you multiply 79.9 times 2 plus magnesium is 24.3. This gives us 184.1. So that's good enough. 1 decimal place. 184.1 grams in 1 mole. We could do the same thing for the other ones like KBr. We'll need that number later on when we try to find out the theoretical yield. So now with KBr, we could go K, again, is 39.1, plus the Br is 79.9. Again, leave out the 2 because we're not looking for 2 moles, we're looking for 1 mole. 39.1 plus 79.9, that'll give you 119.0 grams in 1 mole. Magnesium, again, was right over here, is 24.3 grams per mole. Okay, now we got all the information from the periodic table, which is one very important thing. Remember, we wanted to have in 5 grams of potassium, we want to know exactly how many grams of magnesium bromide we have. Okay, what I've got here is mole potassium is equal to 5.00 gram. We want to convert this to moles, so the conversion factor is actually our molar mass. Remember, our molar mass is grams over mole, 39.1 grams divided by mole. So we want to flip this and say that I'm going to use my fraction. And it's always good to try to learn how to use these equation editors because it makes work look so nice. So 1 mole in 39.1 grams of potassium. We could put K right down here. And we could also say 5 grams of K potassium, 1 mole of K. And you could see that the units cancel, so the grams cancel and we're left with moles. And 5 divided by 39.1 is 0.128. It's actually, on my calculator, it says 0.127877237. Of course, you don't want that many digits. We could keep it to 3 digits because this number of significant figures in grams is only 3. So we'll keep the 3 and our answer will be moles of potassium. And so we put this number right down here where it says moles, 0.128 for that potassium. Okay, now the reason why I like to tabulate this data is you could see when I entered the grams of potassium and the molar mass, and remember from that triangle, grams over the grams per mole gives you the moles. And if you remember from my table right here, grams over grams per mole gives you the mole. If you have this in this order, then you could say grams divided by grams per mole is equal to the mole. Okay, now we need to find this mole for magnesium bromide. Okay, so what I wrote down here is mole of magnesium bromide required. That's this number that we're going to have to react with all of the potassium, 0.128 moles of potassium. So 0.128 moles of potassium times our relationship between the potassium and magnesium. So what we want on top, on the numerator, is the magnesium bromide. That's what we're trying to find. So we'll have 1 mole of this, as shown in our chemical equation. It said that we have a 2-to-1 relationship. So that's why we want 1 mole of the magnesium bromide. Okay, and potassium is 2 moles of potassium. That's where I got from this stoichiometry equation. Remember, our equation was 2K plus mgbr2 going to 2kbr plus mg. And so we only have a half is required to react with all of the potassium, 0.128. So you take 0.128 divided by 2, that'll give you 0.064. 0.064 moles of mgbr2. Okay, and then we could enter this data in our table, 0.064 moles. And to find the grams, notice that the moles times grams per mole will give you the grams. But we could write it down here in the table like this, or we could go ahead and multiply these numbers going up. We'll get a multiply. So 184.1 times 0.064, this will be the number of grams of magnesium bromide that's required. And we only need 3 significant figures. Will be 11.8. My calculator would say 11.78, but we're just going to put 11.8 grams. And that's the amount of magnesium bromide that's required to react with the 5 grams of potassium.